take a deep breath. Go ahead, really do it. Fill your lungs completely. What you just inhaled is about 21% oxygen, 78% nitrogen, and a mix of other gases making up the rest. That's what keeps you alive right now. That's what every breath you've ever taken has given you. But here's something that'll mess with your head. If you could somehow travel back 300 million years and take that same deep breath, it would feel different, powerful, almost intoxicating, because the air itself was different. Earth's atmosphere contained 35% oxygen, not 21%, 35%. If you're using this video to fall asleep, that's exactly why I make these. So maybe subscribe and tell me where you are and what time it is. I check comments and it's like Tokyo at lunch, London at midnight, Sydney at sunrise, all at once. It's kind of beautiful actually. Now, back to that breath. A 14% increase in oxygen doesn't sound like much, right? It's just a number. But that difference transformed Earth into something almost unrecognizable. An alien world where the rules of biology worked completely differently than they do today. Where insects grew to the size of dogs. Where dragonflies had wingspans wider than a hawk. Where millipedes stretched longer than your arm, and plants grew so massive, so impossibly tall, that their fallen remains would eventually become the coal that powered the Industrial Revolution. All of it because of oxygen. Too much oxygen. This period in Earth's history has a name, the Carboniferous. It lasted from about 359 to 299 million years ago. 60 million years of biological experimentation on a scale we can barely comprehend. Before the dinosaurs, before the first mammals, before anything that looks remotely familiar, there was this. An Earth breathing differently. And here's what really keeps scientists up at night. If you could somehow step into that ancient atmosphere as you are now, as a modern human with modern lungs, you probably wouldn't survive very long. See, oxygen is both life-giving and deadly. We need it to survive, but too much of it becomes toxic. It's why scuba divers who go too deep can suffer from oxygen poisoning. Why premature babies in oxygen tents sometimes develop complications. Our bodies are calibrated for 21% oxygen, fine-tuned over millions of years of evolution to handle exactly this atmospheric mixture. Drop the oxygen to 15% and you'd pass out within minutes. Raise it to 35%. And your entire biochemistry would start going haywire. Your cells would be drowning in oxidative stress. Free radicals would tear through your tissues. Within hours, maybe days, your lungs would start to show signs of damage. The very thing keeping you alive would be poisoning you. But for the creatures that lived back then, 35% oxygen wasn't poison. It was opportunity. It was fuel. It was the secret ingredient that allowed life to explode into forms we'd consider impossible today. Because here's the thing about oxygen. It's what powers metabolism. The more oxygen available, the more energy living things can generate. And with more energy, you can do things that normally wouldn't work. You can grow bigger, move faster, develop more complex systems. Push the boundaries of what biology allows. Insects, which breathe through simple tubes called tracheae instead of lungs, hit the jackpot. Without the constraint of low oxygen limiting their size, they grew enormous. Griffinflies, ancient relatives of dragonflies, patrolled the skies with wingspans reaching 5 feet. Imagine something the size of a seagull, but it's an insect. A predator with compound eyes and mandibles that could probably take a chunk out of your hand if you got too close. Arthropods, a millipede-like creature, grew to over 8 feet long. Picture encountering that crawling through the forest undergrowth. Not a dinosaur, not a mammal, an arthropod the size of an alligator. The plants were just as incredible. Forests of giant club mosses and horsetails stretched hundreds of feet into the air, creating the first true forest canopies Earth had ever seen. These weren't the forests we know today. No flowering plants yet, no grass, just an endless sea of green dominated by species that today exist only as small, humble ground cover. But back then, with all the oxygen feeding their growth, they became titans. And all of this, every giant insect, every towering tree, every bizarre creature that crawled or flew through that ancient world existed because Earth's atmosphere had crossed a threshold. Too much oxygen, just enough to rewrite the rules of life completely. The question is, how did it happen? How did Earth's atmosphere transform from something relatively normal to this oxygen-rich world? And maybe more importantly, what made it stop? Because it did stop. Oxygen levels eventually dropped back down. The giants died out. The world returned to something closer to what we know today. This is the story of when Earth breathed differently. And it's going to change how you think about the air filling your lungs right now. Here's something that should terrify you. If you could somehow travel back 3 billion years and step out onto early Earth, your first breath would be your last. Not because the air was too hot or too cold, but because there was essentially no oxygen. Zero. The atmosphere that wrapped around the planet like a blanket was a toxic cocktail of methane, ammonia, carbon dioxide, and water vapor. Everything that keeps you alive today simply didn't exist yet. Think about that for a second. Oxygen. The thing you're breathing right now without even thinking about it. The molecule that powers every cell in your body wasn't always here. Earth spent most of its early history as a planet where oxygen was basically poison to the life forms that existed. And those life forms, primitive single-celled organisms, they liked it that way. But then something happened. Something so catastrophic, so world-changing, that it makes climate change look like a minor weather event. It was called the Great Oxygenation Event, and it was basically the first global environmental disaster. Except this disaster took 200 million years to unfold, and when it was finished, it had completely rebuilt Earth's atmosphere from the ground up. The culprits were tiny, microscopic actually, cyanobacteria. Little blue-green organisms that figured out something revolutionary around 3.5 billion years ago. They learned how to capture energy from sunlight using a process we now call photosynthesis. Take in carbon dioxide, use sunlight to break it apart, build sugars for energy, and release the oxygen as waste. Waste. That's what oxygen was to early life. Toxic waste. Because here's the thing about oxygen. It's incredibly reactive. It tears apart molecules, causes chemical reactions, damages cellular structures. For organisms that had evolved in an oxygen-free world, this waste product was lethal. But the cyanobacteria just kept pumping it out. For hundreds of millions of years, most of that oxygen got absorbed by rocks and dissolved iron in the oceans. Earth had so much iron in its early oceans that the oxygen just reacted with it, forming rust that settled to the ocean floor in massive deposits. These banded iron formations are still visible today, geological evidence of the Great Oxygenation beginning. Then, around 2.4 billion years ago, something shifted. The iron ran out. Or more precisely, there was so much oxygen being produced that it overwhelmed the iron's ability to absorb it. Oxygen began escaping into the atmosphere in significant quantities for the first time. The result was an extinction event. the Great Oxidation Event killed off most of Earth's anaerobic organisms, life forms that couldn't handle oxygen. Entire ecosystems collapsed. Species that had dominated the planet for 1 billion years suddenly found their environment had become toxic. It was, in a very real sense, the first pollution crisis, except the pollution was the very thing that would eventually allow complex life to exist. But oxygen levels didn't just shoot up to modern levels and stay there. That's not how planetary atmospheres work. The rise was gradual, punctuated, full of reversals and sudden changes. For nearly 2 billion years after the Great Oxygenation Event, oxygen levels fluctuated wildly, sometimes rising to maybe 1 or 2% of the atmosphere, sometimes crashing back down to near zero. Earth, during this period, was unstable. Periods of oxygenation would be followed by periods where the oceans became anoxic again. Dead zones where nothing that needed oxygen could survive. The planet was trying to find equilibrium, trying to balance oxygen production against oxygen consumption, and it took almost 2 billion years to figure it out. The breakthrough came with the evolution of eukaryotic cells around 2 billion years ago. These were cells with nuclei, with specialized internal structures, cells that could eventually combine to form multicellular organisms, and critically, many of them could use oxygen for respiration, turning it from waste product into fuel. This created a feedback loop. More oxygen-using organisms meant less oxygen accumulating as waste, but it also meant more organisms that could harvest energy efficiently, allowing them to grow larger and more complex, which meant they needed even more oxygen. For the first time, life wasn't just tolerating oxygen, it was depending on it. Still, oxygen levels remained relatively low for another billion years, maybe 2 to 5% of the atmosphere compared to the 21% we have today. Enough to support simple multicellular life, but not enough for anything really complex. The oceans had oxygen-breathing creatures, but they were small, simple, limited by how much energy they could extract from the thin atmosphere. Then came the game changer, land plants. For the first 3.5 billion years of Earth's history, land was essentially barren. Nothing grew there. Nothing could. It was just rock and sand and maybe some bacterial mats in wet areas. The continents were dead zones, blasted by ultraviolet radiation, with no soil, no protection from the elements. The first plants to colonize land appeared around 470 million years ago, during the Ordovician period. They were simple things, mosses and liverworts, primitive plants that stayed low to the ground and needed to stay wet. But they were photosynthesizing. They were taking in carbon dioxide and pumping out oxygen. Over the next 100 million years, plants got more sophisticated. They developed vascular systems to transport water and nutrients. They developed roots to anchor themselves and extract minerals from rock. They developed lignin, a tough polymer that allowed them to grow tall and woody. By the Devonian period, around 400 million years ago, the first forests were appearing, and forests are oxygen factories. A single large tree can produce hundreds of pounds of oxygen per year. A forest can completely transform the local atmosphere. As plants spread across the continents during the Devonian, oxygen levels began rising steadily for the first time in Earth's history. By 350 million years ago, as the Carboniferous period began, oxygen levels had reached about 25% of the atmosphere. That's already significantly higher than today's 21%. But the rise didn't stop there, because conditions during the Carboniferous created a perfect storm for oxygen accumulation. First, there were the forests themselves. Carboniferous forests weren't like modern forests. They were dominated by massive-scale trees, primitive plants that could grow over 100 feet tall, with trunks several feet thick. Club mosses that would tower over anything you'd see today. And these forests covered enormous areas. Vast wetland forests stretched across what is now North America, Europe, and Asia. These plants were photosynthesizing at an incredible rate, pulling carbon dioxide out of the atmosphere and releasing oxygen. But here's where things got really interesting. The carbon they were pulling out wasn't getting recycled back into the atmosphere. In modern forests, when a tree dies, it falls to the ground and begins to rot. Bacteria and fungi break down the wood, consuming it and releasing the carbon back into the atmosphere as carbon dioxide. This creates a balanced cycle. Carbon captured by living trees, carbon released by dead trees, oxygen rising and falling but staying relatively stable. But Carboniferous forests didn't have that balance, because the organisms that break down lignin, the tough woody material that made up tree trunks, hadn't evolved yet. When a Carboniferous tree fell over, it just sat there, year after year, decade after decade, century after century. The wood didn't rot, it accumulated. In the waterlogged environments where these forests grew, fallen trees would get buried in sediment and compressed over millions of years. The carbon they contained was locked away, first as peat, then as coal. Massive coal deposits, some hundreds of feet thick, layers and layers of compressed ancient forest. This was a one-way street for carbon. Trees pulled it out of the atmosphere, died, got buried, and the carbon stayed buried, which meant the oxygen that had been released during photosynthesis stayed in the atmosphere. There was nothing consuming it, nothing balancing it out. Oxygen levels just kept climbing. 25% became 28%, then 30%, then higher still. By the late Carboniferous, around 300 million years ago, oxygen levels peaked at approximately 35% of the atmosphere. That's 67% higher than the oxygen concentration you're breathing right now. The planet had become hyperoxic, saturated with oxygen at levels never seen before or since. But why did it stop at 35%? If the process was self-reinforcing, if forests kept growing and carbon kept getting buried, why didn't oxygen just keep rising indefinitely until it was 40% or 50% or higher? The answer is fire. Oxygen is what makes things burn. The more oxygen in the atmosphere, the easier it is for fires to start and the hotter they burn. Modern wildfires require sustained temperatures and dry conditions to really get going. But in a 35% oxygen atmosphere, fires would ignite from lightning strikes that would barely cause a spark today. More importantly, in that kind of oxygen-rich environment, even wet vegetation would burn. Wood that was freshly cut, plants that were still green, even living trees could catch fire and burn if the conditions were right. The landscape would have been incredibly flammable. This created a natural ceiling for oxygen levels. As oxygen concentration increased, wildfires became more frequent and more intense. These fires would consume vast amounts of vegetation, releasing carbon dioxide back into the atmosphere and consuming oxygen in the process. When oxygen levels got high enough, the planet would literally burn away the excess. Evidence for this comes from the geological record. Carboniferous coal deposits are full of charcoal, fossilized evidence of ancient wildfires. Some layers show signs of fires so intense they would have created firestorms, massive conflagrations that consumed entire forests. The high oxygen levels that allowed life to grow to enormous sizes also made the world incredibly dangerous. There was also a chemical limit. At oxygen concentrations above about 35%, certain chemical reactions become spontaneous. Materials that normally require high temperatures to ignite can combust at room temperature. The atmosphere itself becomes a fire hazard. Push oxygen levels much higher than 35%, and the entire biosphere becomes unstable, subject to catastrophic burning that would reset the whole system. So 35% became the effective ceiling. Oxygen would rise toward that level, fires would break out across the planet, vegetation would burn, oxygen would drop slightly, forests would regrow, and the cycle would repeat. For tens of millions of years during the Carboniferous, Earth existed in this high oxygen state, balanced precariously between maximum photosynthesis and maximum burning. The atmospheric chemistry of this period was unlike anything before or since. The partial pressure of oxygen, the actual amount of oxygen molecules in a given volume of air, was about 75% higher than today. This meant oxygen diffused into tissues much more easily. It penetrated deeper into bodies, reached cells more efficiently, enabled biological processes that would be impossible in modern air. This is what allowed insects to grow to enormous sizes. This is what made the Megafauna possible. This is what transformed Earth into a planet of giants. Because for the first time in planetary history, there was enough oxygen to power large, active, energy-intensive life forms. The limiting factor that had kept organisms small and simple for billions of years had been removed. But the high oxygen world wasn't stable. It couldn't be. It was an anomaly, a temporary state created by a unique combination of factors that wouldn't last. The forests that created it were already sowing the seeds of its destruction. Evolution was working on organisms that could break down lignin. Climate was shifting. The conditions that had allowed coal forests to dominate were beginning to change. The age of 35% oxygen would last about 50 million years, from roughly 325 to 275 million years ago. In geological terms, that's a brief moment, a flash of hyperoxia in Earth's long history. But during that brief moment, life exploded into forms that would never exist again. The oxygen revolution had reached its peak, and the world would never be the same. Picture this. You're walking through a Carboniferous forest 300 million years ago. The air is thick, almost syrupy with oxygen. Every breath fills your lungs with 35% pure O2, compared to the 21% you're used to. You feel alert, energized, like you've just had 3 cups of coffee. Then you hear it, a sound like a helicopter approaching. You look up, and there, descending through the canopy, is something that should not exist. It's a dragonfly, except it's not dragonfly-sized. Its wingspan stretches nearly 2.5 feet across, wider than a hawk, bigger than any bird that exists in this period. Its compound eyes, each containing thousands of individual lenses, lock onto you with the precision of a guided missile. This is Meganeura, and in this world of abundant oxygen, it is an apex predator. But here's the thing that makes this moment truly terrifying. It's not alone. The Carboniferous sky is thick with giants. Dozens of Meganeura patrol the airspace above the forest like fighter jets. They're hunting smaller insects, yes, but they're also hunting each other. And they're hunting anything else that moves, including you, if you were small enough. These aren't the delicate dragonflies of modern ponds and streams. These are armoured killing machines with mandibles powerful enough to crunch through the exoskeletons of other insects. They can fly at speeds approaching 30 miles per hour. They can hover, reverse direction instantly and strike with surgical precision. and they've been perfected by 50 million years of evolution in a high-oxygen world. You watch as one Meganeura spots a smaller insect, probably something the size of a modern sparrow. The pursuit lasts less than 3 seconds. The Meganeura intercepts its prey mid-flight with movements so fast your brain barely registers them. There's a crunch of chitin, and it's over. The giant dragonfly settles on a nearby tree branch to consume its meal, its enormous wings catching the light like stained glass windows. But the sky isn't the only place where giants rule this world. You hear something else now, a rustling in the leaf litter behind you. You turn slowly, and what you see makes every nightmare about insects seem quaint by comparison. Moving through the undergrowth is something that looks like it escaped from a science fiction film. It's segmented, armoured, supported by dozens of legs that move in perfect rippling coordination. It's an Arthropods, and it's longer than you are tall, 8 feet from head to tail, as thick around as your thigh. The largest land invertebrate that has ever existed. Now, here's where your modern instincts betray you. You see something that looks like a giant millipede, and part of your brain says, "Millipedes eat rotting plants, you're fine, stay calm," and you'd be right. Arthropods was probably a herbivore or detritivore. Probably. The problem is, we're not entirely certain, because when you scale a millipede up to the size of an adult human, all bets are off. Those mandibles that delicately nibble on decomposing leaves when you're an inch long, when you're 8 feet long, they're powerful enough to process tree bark, roots, and who knows what else. The Arthropods moves past you with surprising speed for something so massive. Each of its segments is plated with thick chitin, darker than mahogany, harder than fingernails. You can hear it breathing through the spiracles along its body, tiny openings that connect to an internal network of tubes called tracheae. And this is where the story gets really interesting, because the reason this creature can exist, the reason Meganeura can fly with a 2.5-foot wingspan, the reason this entire world of giant insects is possible, comes down to one simple fact. Insects breathe differently than you do. You have lungs, complex organs with massive surface area for gas exchange, blood that carries oxygen to every cell in your body, an entire cardiovascular system designed to move oxygen where it needs to go. Insects don't have any of that. They breathe through passive diffusion. Air enters through spiracles, tiny holes along their body segments. From there, it travels through increasingly smaller tubes called tracheae and tracheoles. Eventually, these tubes become so small, so numerous, that they deliver oxygen directly to individual cells. No lungs, no blood transport, just physics. And physics is where the limitation comes in. In normal atmospheric conditions with 21% oxygen, this system works great when you're small. An ant, a mosquito, a housefly, perfect. The oxygen can diffuse quickly enough through those tiny tubes to supply every cell in their body. But start scaling up, and you run into problems. Diffusion is slow. The rate at which gas molecules move through tubes doesn't scale linearly with body size. When you double an insect's length, you quadruple its surface area, but you increase its volume by 8 times. This is called the square cube law, and it's the reason we don't have dog-sized spiders today. As an insect gets bigger, the distance oxygen needs to travel to reach its innermost cells increases. But the amount of oxygen entering through the spiracles doesn't increase proportionally. Eventually you hit a wall where the insect's internal tissues start suffocating, because oxygen can't diffuse quickly enough to supply them. In 21% oxygen, that wall comes pretty fast. There are good mathematical models that show insects in modern atmosphere basically can't grow larger than the biggest beetles we see today, maybe 6 inches long at the absolute maximum. Push beyond that size, and their core tissues would be hypoxic, starved of oxygen, unable to generate the energy needed for basic metabolism, but increase atmospheric oxygen to 35%, and everything changes. Suddenly the concentration gradient driving diffusion becomes much steeper. Oxygen molecules are packed more densely in the air, diffusing into the tracheae faster. The rate at which oxygen travels through those internal tubes increases dramatically. That size wall gets pushed back, way back. Insects that would suffocate at 6 inches in modern atmosphere can grow to 12 inches, 18 inches, or in the case of Arthropods, 8 feet without their core tissues running out of oxygen. The Carboniferous atmosphere didn't just allow giant insects to exist, it practically demanded them. Because here's what happens when you're an insect and suddenly you can grow larger without suffocating. You gain massive advantages. Larger body size means better temperature regulation. It means you can store more energy, survive longer periods without food. For predators like Megafauna, it means you can take down larger prey. For herbivores like Arthropods, it means you can process tougher plant material and access food sources smaller insects can't exploit. Most importantly, it means you're harder to kill. When you're a small insect, everything wants to eat you. Birds, amphibians, other insects, even plants have ways to catch and consume you. But grow to the size of a hawk or a full-grown human, suddenly you're not prey anymore, you're a predator, you're an apex organism, you're an ecosystem engineer. And the fossil record shows these giants didn't just exist, they dominated. Megafauna fossils have been found across what was then the supercontinent of Pangaea. From North America to Europe, these giant dragonflies ruled the skies. Paleontologists can tell from wingwear patterns that they were active, powerful flyers, not clumsy accidents of evolution, but refined aerial predators. Some specimens show evidence of territorial behavior, damage patterns suggesting they fought each other for prime hunting grounds. The prey items they were hunting, other giant insects. The Carboniferous wasn't just home to giant dragonflies and millipedes. The entire insect world had scaled up. There were mayflies with 8-inch wingspans, cockroaches the size of your hand, possibly longer, primitive relatives of crickets that would have dwarfed modern species, and where there are herbivorous insects, there are predators to eat them. Enter the giant scorpions. Now technically, the largest scorpions of this period weren't quite as enormous as Arthropods. They maxed out around 27 inches, maybe 2 feet in exceptional specimens. But here's the thing about a 2-foot scorpion with claws the size of your fist, and a stinger as long as your finger. Size isn't everything when you're built like an armoured tank with chemical weapons. These weren't the desert scorpions of today, hiding under rocks and hunting at night. Carboniferous scorpions were active predators, hunting in the leaf litter and along stream banks. Some species were aquatic or semi-aquatic, ambush predators waiting for fish or amphibians. Their venom, scaled up with their body size, would have been potent enough to take down prey many times their own size. And then there were the spiders. We have less direct fossil evidence for giant spiders because spiders don't fossilize as well as insects with hard exoskeletons. But we know they existed because we've found their prey. More importantly, we've found their burrows, trace fossils showing silk-lined tunnels in Carboniferous sediments, some large enough that the spiders who made them must have had leg spans of 18 inches or more. These were probably ambush hunters, like modern trapdoor spiders, but scaled up to nightmare proportions. Imagine walking through that Carboniferous forest and stepping too close to a concealed burrow. the trapdoor explodes open. Something with 8 legs, each as thick as your finger, erupts from underground with speed that makes you understand why spiders are apex predators in miniature ecosystems. Except this one isn't miniature. This one is large enough to take down vertebrates. The ecological implications of these giant arthropods were profound. Arthropleura, despite probably being an herbivore, would have been an ecosystem engineer. Something that large moving through the forest floor constantly. It's churning soil, breaking down plant material, creating pathways through dense vegetation. Every time an Arthropleura died, it represented a massive influx of nutrients into the decomposer food web. Its feeding behavior would have shaped plant communities, creating patterns of herbivory that affected which species could successfully reproduce. Meganeura and the other giant aerial predators controlled insect populations from above. Any herbivorous insect that got too abundant would attract the attention of these aerial hunters. This created what ecologists call top-down control, where predators regulate the populations of prey species, which in turn affects plant communities. The presence of giant dragonflies would have prevented any single insect species from completely overwhelming the vegetation. The giant scorpions and spiders provided a different kind of control, operating in the leaf litter and understory. They were eating smaller arthropods, yes, but also amphibians, small reptiles, anything they could overpower. This put them in direct competition with vertebrate predators, creating complex food web dynamics we can only begin to reconstruct from the fossil record. But here's what makes the Carboniferous megafauna even more remarkable. They weren't evolutionary flukes. They weren't accidents that survived despite their size. They were successful, dominant organisms that thrived for tens of millions of years. The fossil record shows Meganeura and its relatives persisted for at least 50 million years. Arthropleura existed for even longer, from roughly 340 to 280 million years ago. These weren't brief experiments. These were evolutionary success stories, proof that when conditions are right, insects can compete with vertebrates for dominance of terrestrial ecosystems. And we know this because of some remarkable fossil discoveries. In 1979, a paleontologist named Graham Woodward was examining Carboniferous rocks in Derbyshire, England. He found something that would change our understanding of this ancient world, a complete Arthropleura fossil preserved in stunning detail, not just the hard external shell, but evidence of internal organs, the arrangement of legs, even traces of the tracheal system. This specimen was over 6 feet long, and it was clearly not fully grown. Since then, additional discoveries have filled in the picture. We've found Meganeura wings preserved so perfectly that we can see individual vein patterns. We've found trackways showing how Arthropleura moved, the distinctive parallel grooves left by its many legs. We've found fossil forests, with the damage patterns these giant herbivores left on bark and roots. Most tellingly, we found the burrows. In Pennsylvania and Illinois, paleontologists have discovered trace fossils called beaconites, spiraling burrows that descend several feet into Carboniferous sediments. These are believed to be Arthropleura burrows, places where these giants sheltered from predators or extreme weather. Some show evidence of repeated use, suggesting these creatures had home territories, places they returned to generation after generation. The preserved burrows tell us something else important. They show Arthropleura had complex behavior, something that makes a permanent burrow, that invests energy in creating shelter, that returns to the same location repeatedly. That's not simple stimulus-response behavior. That's sophisticated for an invertebrate. It suggests these giants had sensory systems capable of navigation and memory, neural systems complex enough to support what we might carefully call intelligence. And maybe that shouldn't surprise us, because high oxygen doesn't just allow larger body size, it allows more energy-intensive neural tissue. The same atmospheric conditions that permitted giant bodies would have permitted more complex nervous systems, better eyes, faster neural processing speeds. These weren't just big insects, they were smarter insects, operating with neural sophistication that modern insects, constrained by lower oxygen, can't match. But the megafauna weren't just affecting their own ecosystems, they were shaping the evolution of every other organism around them. Early amphibians and reptiles had to adapt to a world where insects could fight back, where prey items could be dangerously large, where the sky contained predators capable of snatching small vertebrates. This created selection pressures that drove the evolution of defensive adaptations, thicker skin, faster reflexes, better vision for detecting aerial threats. The plants had to adapt too. Being eaten by an insect the size of a human is very different from being nibbled by something the size of your thumb. Some plant species developed tougher bark, chemical defenses specifically targeted at arthropod herbivores, growth patterns that made them less vulnerable to the systematic defoliation that arthropluera-sized herbivores could inflict. The entire Carboniferous ecosystem was shaped by the presence of these giants. They were keystone species, organisms whose impact on their environment was disproportionate to their actual numbers. Remove them, and the whole system would collapse and reorganize into something completely different, which is exactly what eventually happened. But that's getting ahead of the story. For now, for tens of millions of years, the Age of Giants continued. Meganeura patrolled the skies, Arthropleura churned through the forest floor, giant scorpions stalked the shadows, enormous spiders waited in silk-lined burrows. The whole planet was an alien world where arthropods, not vertebrates, were the true masters of the land, and it was all made possible by one simple fact. The air was different, richer, more energetic, capable of supporting life at scales that seem impossible today. Oxygen at 35% had broken the size constraints that normally limit insect body plans. It had created evolutionary possibilities that would never exist again. The giants walked, crawled, and flew across a world that would have been incomprehensible to any modern observer. A world where the fundamental rules of ecology were written differently, where being an invertebrate wasn't a limitation but an advantage, where the largest predators had compound eyes and exoskeletons and mandibles instead of teeth. This was Earth in the Carboniferous, and the giants were only the beginning of how high oxygen transformed life on this planet. Now here's where things get really strange. Because while giant dragonflies were terrorizing the skies and millipedes the size of alligators were crawling through the undergrowth, something even more transformative was happening at ground level. The Carboniferous forests were growing in ways that would quite literally reshape the planet's future. And I mean that in the most direct sense possible. Those forests are now mountains, mountains of coal buried under entire continents. Picture this. You're standing at the edge of a Carboniferous swamp forest around 320 million years ago. The air is thick, humid, and oxygen-rich, about 35% oxygen compared to today's 21%. Every breath feels almost intoxicating, like you're breathing pure energy. And stretching before you, as far as you can see in every direction, are trees. But not trees like anything alive today. These are lepidodendron, scale trees, and they're absolutely massive. The largest ones tower 130 feet into that oxygen-saturated sky. Their trunks can reach 6 feet in diameter at the base. They're covered in a distinctive diamond-patterned bark that gives them their name, like the scales of some enormous reptile turned to wood. Except, here's the thing, they're not really trees at all, not in the way we understand trees today. Lepidodendron were giant club mosses, relatives of the tiny moss-like plants you might see growing in damp corners of your basement. Except, evolution, drunk on oxygen and favourable conditions, had scaled them up to absurd proportions. They grew tall through a completely different strategy than modern trees use. Their trunks weren't made of solid wood all the way through. Instead, they were mostly hollow, with a thin cylinder of supportive tissue around the outside, like an enormous straw covered in bark. This made them incredibly efficient at growing tall quickly, but also made them vulnerable. Strong winds could snap them like toothpicks, and they did, constantly. The forest floor was a chaotic mess of fallen giants, broken trunks, and uprooted stumps. But it didn't matter, because these scale trees could grow from spore to full height in just 10 to 15 years. For comparison, a modern oak tree might take 50 years to reach half that height. The Carboniferous forests were growing, dying, and regrowing at a pace that modern forests couldn't match. But the really weird part was what happened to the trees when they died. In a modern forest, when a tree falls, it starts decomposing almost immediately. Fungi, bacteria, insects, they all attack the dead wood, breaking it down into simpler compounds that return nutrients to the soil. The carbon that the tree pulled from the atmosphere during its life gets released back as CO2. This cycle completes. Death feeds new life. The Carboniferous forest didn't work that way. Because here's the thing. Those scale trees had evolved something revolutionary, something that would change the entire planet's climate and create the fossil fuel deposits that would power human civilization 300 million years later. They had evolved lignin. Lignin is the compound that makes wood hard. It's a complex organic polymer that provides structural support, helps transport water, and makes plant tissue tough and resistant to damage. Modern trees are full of it. It's what makes wood woody. But lignin has a problem. It's really hard to break down. The molecular structure is incredibly complex, with cross-linked polymers that resist most forms of chemical degradation. Breaking down lignin requires specialized enzymes that, in the Carboniferous period, didn't exist yet. The fungi that decompose wood today took millions of years to evolve the biochemical tools to break down lignin. In the Carboniferous, those tools hadn't been invented yet. Evolution was still working on the problem. So when those massive scale trees died and fell into the swamps, they just stayed there, year after year, century after century, millennia after millennia. Dead trees piling up, layer upon layer, faster than anything could decompose them. The swamps helped preserve them too. When a tree fell into standing water, low oxygen levels at the bottom of the swamp slowed what little decomposition could occur. The tree would sink, get covered by sediment, and effectively be sealed away from the atmosphere. Another tree would fall on top, then another, and another. The forests were literally burying themselves. Imagine walking through one of these swamp forests. The ground beneath your feet isn't solid soil. It's a soggy mass of partially decayed plant matter, compressed under its own weight. Step wrong and you might sink up to your waist in ancient vegetation. The smell would be overwhelming. Part forest, part swamp, part something else entirely. The chemical smell of plant compounds that nothing has yet learned to digest. And these weren't small forests. They covered entire continents. Vast stretches of what is now North America, Europe, and Asia were blanketed in carboniferous swamp forests. Millions upon millions of square miles of scale trees and giant club mosses, all growing frantically in that oxygen-rich atmosphere, all dying and piling up faster than they could decay. The scale of it is almost impossible to comprehend. In some regions, layers of dead plant matter accumulated to depths of hundreds of feet. Entire forests compressed and preserved stacked on top of each other. As more sediment piled on top, pressure and heat began transforming the plant matter, first into peat, then into lignite, eventually into bituminous coal, and even anthracite in regions where pressure and temperature were highest. Every coal seam we mine today represents an ancient forest. The coal in Appalachia, formed from forests that grew where mountains now stand. The vast coal deposits of the Ruhr Valley in Germany, the forest that covered what was then a low-lying tropical swamp. The coalfields of China, Russia, Australia, all of them are compressed carboniferous forests, converted over millions of years into concentrated carbon. When you burn coal, you're releasing carbon that was pulled from the atmosphere 300 million years ago. Carbon that was locked away when those scale trees died and fell into swamps. Carbon that would have stayed in the atmosphere as CO2 if fungi had evolved lignin-digesting enzymes just a few million years earlier. The entire Industrial Revolution was powered by this evolutionary timing accident. But while this was happening, while forests were burying themselves and creating future mountains of coal, they were also doing something even more dramatic to the atmosphere. They were pumping it full of oxygen. Remember, photosynthesis pulls carbon dioxide from the air and releases oxygen. Every tree growing in those vast forests was an oxygen generator, and because the carbon wasn't being released back into the atmosphere through decomposition, the oxygen just kept accumulating. This created a feedback loop. More oxygen meant plants could grow bigger and faster. Bigger plants meant more photosynthesis. More photosynthesis meant even more oxygen. The atmospheric oxygen concentration climbed from around 21%, similar to today, to as high as 35% over the course of tens of millions of years. The carboniferous forests were terraforming their own planet. Plant reproduction in this environment became increasingly elaborate. Modern trees produce seeds, which are self-contained packages of nutrients and genetic material that can survive harsh conditions and germinate when circumstances are right. The carboniferous scale trees were still using the more primitive spore system. They produced spores, microscopic reproductive cells that needed moisture to develop into new plants. But they produced them in absolutely staggering quantities. The fossil record preserves cone-like reproductive structures from scale trees that could be over 2 feet long, packed with millions of spores. When these cones released their spores, the air would have been thick with them, like yellow clouds drifting through the forest. Most would never germinate. They'd fall into water, land on rocks, or get eaten by insects. But with millions of spores from thousands of trees, enough would find suitable conditions to keep the forest regenerating. This reproductive strategy was wasteful by modern standards. Seeds are far more efficient. But in the Carboniferous, efficiency wasn't the point. Resources were abundant. The high oxygen content made energy cheap. Plants could afford to be wasteful. Better to produce millions of spores and guarantee some survived than to carefully nurture a few seeds. Some carboniferous plants did begin experimenting with seed-like structures. The seed ferns, plants that looked like ferns but reproduced with primitive seeds, were among the first. They represented an evolutionary transition. plants beginning to develop the more efficient reproductive strategies that would dominate later periods. But they were still minority players. The spore-producing scale trees and giant club mosses were the dominant life forms. The forest structure itself was alien by modern standards. Most carboniferous trees didn't branch the way modern trees do. They grew straight up, sometimes over 100 feet, before finally producing a crown of branches at the very top. The forests would have looked like enormous fields of telephone poles with bushy tops. Very little vegetation below, just massive trunks rising from the swampy ground. This created a strange ecosystem structure. The forest floor was dim and wet, dominated by smaller ferns, early seed plants, and the arthropods that fed on decaying plant matter. The mid-story was nearly empty, just endless trunks. And the canopy, way up at the top, was where most of the action happened. That's where the giant dragonflies hunted, where early reptiles climbed to escape predators, where most of the photosynthesis occurred. But perhaps the most important players in this ecosystem were the ones you couldn't see, the plants themselves, invisible architects of global climate change. Every year, those carboniferous forests pulled billions of tons of carbon dioxide from the atmosphere. Most of it was stored temporarily in living tissue, but a significant fraction, the fraction that ended up in those swamps, got locked away permanently, or at least for the next 300 million years. Climate scientists today estimate that the carboniferous forests removed enough CO2 from the atmosphere to drop global temperatures significantly. The early Carboniferous was warm and tropical. By the late Carboniferous, ice sheets were forming at the poles. The forests had literally cooled the planet through their inability to decompose. This raises a fascinating question. If those fungi had evolved lignin-digesting enzymes earlier, would the Carboniferous oxygen spike have happened at all? Probably not. The carbon would have stayed in the atmosphere as CO2. Oxygen levels would have remained stable. The age of giants might never have occurred. Evolution would have taken a completely different path. Instead, we got this weird window in Earth's history, where forests outpaced decomposition, where dead trees piled up faster than anything could break them down, where carbon got buried on a continental scale, and where, as a result, oxygen concentrations reached levels that would transform life in ways that were both spectacular and ultimately unsustainable. Because here's the thing about those coal deposits. They weren't just storing carbon, they were storing the raw materials of the carboniferous forests, the nitrogen, phosphorus, and other nutrients that those plants had pulled from the soil. As millions of square miles of forest got buried, they took those nutrients with them. The soil became progressively depleted. Eventually, this would contribute to the collapse of the carboniferous ecosystem. But that was still millions of years in the future. For now, the forests continued their relentless growth, pulling carbon from the sky, pumping oxygen into the air, building mountains of future coal that wouldn't see daylight again until humans invented mining. All because some plants learned to make wood and nothing yet knew how to rot it away. The carboniferous forests were an accident of evolutionary timing, but they were an accident that would shape the planet's atmospheric composition for hundreds of millions of years, and ultimately they would provide the energy that would power human civilization's transformation of that same atmosphere. The carbon those forests locked away, we've been burning it for the past 2 centuries, releasing it back into the air at a rate about 10,000 times faster than it was originally buried. In a very real sense, we're undoing the Carboniferous, running the process in reverse. Those ancient forests spent 60 million years pulling carbon from the sky. We're putting it all back in just a few centuries, but that's a story for later. For now, just appreciate the sheer weirdness of it all. Forests that couldn't decompose, trees that piled up into mountains, and an atmosphere growing richer in oxygen with every passing millennium, setting the stage for the creatures that would evolve to breathe it. But here's where things get really interesting. While insects were exploding into giant proportions, vertebrates, the animals with backbones, our distant ancestors, they were present in this oxygen-rich world too. And you'd think they'd follow the same pattern, right? More oxygen equals bigger animals across the board. Except they didn't. Not really. Sure, there were some impressively large amphibians stalking the Carboniferous swamps, but we're talking maybe 6-7 feet long. Not exactly the proportional equivalent of a 2-foot-long dragonfly. If vertebrates had scaled up the way insects did, we'd be looking at crocodile-sized salamanders the length of buses, land vertebrates as massive as elephants roaming forests 320 million years ago. But that's not what happened. The reason comes down to basic anatomy, to the fundamental differences in how vertebrates and arthropods are built. Remember, insects breathe through spiracles, those tiny tubes that deliver oxygen directly to tissues through passive diffusion. The more oxygen in the air, the deeper those tubes can penetrate, the larger the insect can grow. It's a direct, almost mechanical relationship. More atmospheric oxygen equals proportionally larger maximum body size. Vertebrates don't work that way. We have active respiratory systems, lungs that pump air in and out, blood that carries oxygen to tissues, hearts that circulate that blood throughout the body. This system is incredibly efficient, but it's also fundamentally different. It's not constrained by atmospheric oxygen levels in the same way insect respiration is. Think of it like this. An insect breathing in 35% oxygen versus 21% oxygen is like the difference between trying to breathe through a straw underwater versus having a proper snorkel. It's a massive improvement, a complete game changer that allows fundamentally different body sizes. But a vertebrate breathing 35% oxygen versus 21% oxygen, that's more like having a really good ventilation system versus a pretty good ventilation system. It's an advantage, definitely. Your cells get oxygen more easily. Your metabolism can run a bit more efficiently. But it doesn't remove a fundamental size constraint the way it does for insects. Vertebrates were already pretty good at getting oxygen to their tissues at 21%. At 35%, they were just better at it. Not different, just better. So instead of growing dramatically larger, vertebrates did something else entirely. They diversified. They adapted. They evolved new survival strategies that took advantage of the oxygen-rich world in more subtle, more sophisticated ways. The Carboniferous period, roughly 359 to 299 million years ago, was when vertebrates really began their conquest of land. Before this, vertebrates were mostly aquatic. Fish dominated the waters, and a few adventurous amphibians were tentatively exploring shorelines, still tied to water for reproduction. But during the Carboniferous, everything changed. The vast coal swamps that covered much of the planet created a mosaic of habitats: deep water channels, shallow marshes, seasonally dry areas, and genuinely terrestrial forests. This environmental complexity drove explosive evolution in early tetrapods, the four-limbed vertebrates that were our ancestors. The amphibians of the Carboniferous swamps were the apex predators of their world. Creatures like Proterogyrinus, a 6-foot-long carnivore with a skull built for crushing, patrolled the waterways like scaled, cold-blooded alligators. Its body was heavy and muscular, designed for ambush hunting in oxygen-rich waters. And that's the key detail. oxygen-rich waters. Because here's what 35% atmospheric oxygen did for aquatic environments. It meant the water itself held significantly more dissolved oxygen. Swamps and marshes, which normally become oxygen depleted as organic matter decomposes, could support much larger populations of aquatic animals. For amphibians that still needed to return to water regularly, this was huge. It meant they could grow larger without worrying about suffocating in stagnant pools. It meant their tadpoles, which breathe through gills, could survive in conditions that would be lethal at modern oxygen levels. The oxygen-rich water acted as a kind of safety net, allowing amphibian diversification even in marginal aquatic habitats. Creatures like Eriops, a 5-foot amphibian with a skull the size of a microwave, thrived in these conditions. Fossil evidence shows it was built like a tank, with thick bones and powerful jaws capable of crushing anything it could catch. It probably spent most of its time in shallow water, using the buoyancy to support its massive body while hunting fish, smaller amphibians, and probably the occasional giant millipede that wandered too close to the water's edge. But the real revolution wasn't happening in the water, it was happening on land. Because while amphibians were dominating the swamps, a new group of vertebrates was emerging. Animals that didn't need to return to water to breed. Animals with a technological innovation that would eventually lead to dinosaurs, birds, mammals, and eventually you. The amniotic egg. It sounds technical and boring, but this was one of the most important evolutionary innovations in vertebrate history. Before the amniotic egg, vertebrate reproduction was tied to water. Amphibians had to lay their eggs in ponds or marshes because their eggs were essentially unprotected, surrounded by a jelly-like coating that would dry out on land. The amniotic egg changed everything. It had a hard or leathery shell that prevented water loss. Inside, a series of membranes protected the developing embryo, stored waste, and provided nutrition. It was a completely self-contained life support system. For the first time, vertebrates could reproduce far from water. They could colonize upland forests, arid regions, anywhere they could find food and shelter. The animals that developed this innovation were the early reptiles, and they appeared in the fossil record around 320 million years ago. Creatures like Hylonomus, a small, lizard-like animal about 8 inches long, found preserved in fossilized tree stumps in what is now Nova Scotia. It wasn't impressive by size. It couldn't compete with the giant amphibians in the swamps, but it didn't have to. It was exploiting an entirely different ecological niche. Hylonomus and its relatives could hunt insects in the leaf litter of upland forests. They could shelter in hollow logs and rock crevices. They could go their entire lives without entering deep water. For animals this small, living in a world of giant dragonflies and foot-long millipedes, being able to hide in places amphibians couldn't reach was a massive survival advantage. And here's where the high-oxygen environment gave them an edge, though not in the way you might think. Reptiles have more efficient lungs than amphibians. Amphibians supplement their lung breathing with cutaneous respiration, breathing through their skin. This works fine, but it means they need to keep their skin moist, which limits how far from water they can venture and how long they can stay active in dry conditions. Reptiles abandoned cutaneous respiration entirely. They developed scaly, waterproof skin that prevented moisture loss. Their lungs became the sole organs of respiration, and they became very good at it. In a 35% oxygen atmosphere, this efficiency meant reptile metabolism could operate at higher levels than would be possible at modern oxygen concentrations. This gave them endurance. They could maintain activity levels longer than amphibians. They could hunt more persistently, travel greater distances, defend larger territories. In a world where forests stretched for thousands of miles, the ability to range widely was crucial. It meant reptiles could find isolated pockets of resources, exploit seasonal food sources, and avoid competition with larger predators. But living in 35% oxygen wasn't all advantages. There were serious challenges, especially when it came to one particular hazard: fire. Because here's what high atmospheric oxygen does to wildfire frequency and intensity. It makes the world incredibly, terrifyingly combustible. At modern oxygen levels around 21%, forests burn when conditions are right. Dry seasons, lightning strikes, accumulated dead vegetation. But there are natural limits. Wetwood doesn't burn easily. Living trees resist ignition. Fires eventually run out of fuel or hit natural fire breaks. At 35% oxygen, those limits essentially disappear. Wood that would smoulder at modern oxygen levels bursts into flame. Fires that would burn slowly at 21% oxygen race through forests at incredible speeds. Even living vegetation can ignite under the right conditions. Research has shown that at oxygen concentrations above 25%, wildfire frequency increases exponentially. At 35%, you're looking at a world where forests burn regularly, catastrophically, and with intensity that would seem apocalyptic by modern standards. Charcoal deposits from the Carboniferous period confirm this. Massive layers of fossilized charcoal, evidence of wildfires that swept across entire regions, reducing those towering scale trees to ash and carbon. Some of these fires probably burned for months, consuming thousands of square miles of forest in single conflagrations. For vertebrates living in this environment, fire wasn't an occasional disaster. It was a constant ecological factor, something that shaped behavior, habitat selection, and evolution itself. Amphibians tied to swamps and marshes had some protection. When fires came through, they could retreat to water. Their moist skin wouldn't ignite easily. They could wait out the firestorm and emerge when it passed. But reptiles living in upland forests faced a much more serious challenge. They couldn't hide underwater. Their scaly skin might protect them from moisture loss, but it wouldn't save them from fire. So they adapted in different ways. Some species became fossorial, developing the ability to dig burrows deep enough to escape surface fires. Fossil evidence shows early reptiles with robust limbs and reinforced skulls suitable for burrowing. Others became more mobile, developing longer limbs and more efficient locomotion that allowed them to flee from approaching fires. There's evidence that some early reptiles were surprisingly fast for their size, capable of sustained running that would have let them escape all but the fastest-moving firestorms. Most importantly, they probably became behavioral opportunists, learning to exploit post-fire landscapes. Because while fires were devastating, they also created opportunities. Burned forests became open habitats with reduced competition. Insects that survived by burrowing or flying away from fires would emerge to feed on new plant growth. Early reptiles that could quickly colonize burned areas would find abundant food and few predators. This created a kind of evolutionary arms race. Fire selected for mobility, for burrowing ability, for behavioral flexibility. Reptiles that could survive fires and exploit their aftermath had massive reproductive advantages. Over millions of years, this pressure refined reptile survival strategies, making them increasingly independent from stable, fire-safe habitats. By the late Carboniferous, around 310 million years ago, early reptiles had diversified into multiple lineages. Some remained small insect eaters, others grew larger, developing the ability to hunt other vertebrates. A few lineages even began developing specialized diets, becoming the first herbivorous land vertebrates, animals capable of directly exploiting the vast plant resources of carboniferous forests. And through it all, they were breathing that oxygen-rich air, running metabolisms that were supercharged compared to what modern reptiles can achieve. Studies of living reptiles in artificial high-oxygen environments show increased stamina, faster growth rates, improved healing, and enhanced immune function. The early reptiles living in natural 35% oxygen would have experienced all these benefits without even knowing they were exceptional, but they were still playing supporting roles in the carboniferous ecosystem. The giant insects were the dominant small predators. The massive amphibians ruled the waterways. The forests themselves, those enormous scale trees and tree ferns, were the real titans of the age. Reptiles were present, diversifying, evolving, but they weren't yet the dominant land vertebrates. That would come later, after everything changed. After the oxygen levels began to decline and the world's combustibility decreased, after the coal swamps dried up and the giant insects began to shrink. In the world that came after the Carboniferous, reptiles would inherit the earth. But for now, they were just small survivors in a world of giants, learning to navigate a landscape that burned and regrew in endless cycles, breathing air that was richer than anything their descendants would ever know. But here's where the Carboniferous gets really wild. All that oxygen being pumped into the atmosphere by those vast coal forests. It created a world that was essentially a bomb waiting to explode. Because oxygen isn't just the stuff we breathe. It's the stuff that makes things burn. And at 35% atmospheric oxygen, compared to today's 21%, Earth had become the most flammable planet in its history. Think about it. Every percentage point increase in oxygen concentration makes combustion exponentially easier. At our current 21% oxygen, you need a sustained heat source to get most organic material burning. At 25%, things start getting dicey. At 30%, wet wood will burn. At 35%, the Carboniferous world was basically soaked in lighter fluid. Lightning strikes that today would just singe a tree could ignite infernos that would rage for months. A single spark from rocks grinding together during a landslide could start a firestorm. Even the spontaneous combustion of decaying plant matter, which releases heat, could trigger massive blazes under the right conditions. And lightning strikes were constant. The Carboniferous wasn't just oxygen-rich. It was also humid, with massive storm systems rolling across those endless swamp forests. Electrical storms were probably more frequent and more violent than anything we see today, each one dropping thousands of lightning bolts across landscapes that were essentially giant tinderboxes. The fossil record preserves the evidence of what happened next. Layers upon layers of charcoal, fossilized ash, burn marks on ancient tree trunks. When paleobotanists examine Carboniferous coal deposits, they find something remarkable. Charcoal everywhere. Not occasional deposits that might indicate rare fires, but constant recurring evidence of burning. Some estimates suggest that up to 70% of all plant material from the Carboniferous shows evidence of fire damage at some point. This wasn't like modern forest fires, where blazes burn through an area and then it takes decades for the forest to recover. In the high oxygen atmosphere of the Carboniferous, fires burned hotter, faster, and more completely than anything in modern times. Temperatures that would make modern wildfires look like candles. Flames that could consume entire forests in days. But here's the really crazy part. The oxygen paradox. Those forests, those incredible coal-producing forests that covered the planet, they were creating the exact conditions that would destroy them. Every ton of coal locked away underground meant more oxygen released into the atmosphere. More oxygen meant more frequent and more intense fires. More fires meant more forests burning. It was a self-reinforcing cycle that should have destroyed the entire system, except it didn't. The Carboniferous forests persisted for over 60 million years, despite burning constantly. How? Evolution, doing what it does best, turning a catastrophe into an opportunity. Some plants developed thick, fire-resistant bark. Fossil tree trunks from the Carboniferous show bark layers that were sometimes a foot thick, far more than what trees need for structural support or water retention. This was armor, protection against the flames that swept through regularly. Other plants evolved rapid regeneration strategies. Some Carboniferous species show evidence of specialized root systems that could survive underground even when everything above the surface burned. Then, when conditions cooled, they'd send up new shoots, reclaiming the burned territory before competitors could move in. Still, others developed fire-dependent reproduction strategies, similar to modern plants like eucalyptus or lodgepole pines. Some Carboniferous seed ferns appear to have required fire to trigger germination. Their seeds had thick, heat-resistant coatings that would only crack open after exposure to intense temperatures. This meant their offspring would sprout immediately after a fire, when competition was minimal and nutrients from ash were abundant. Fire was becoming part of the ecology, not a disaster, but a predictable environmental factor that species could adapt to. But for every species that adapted, dozens went extinct. The Carboniferous fossil record shows wave after wave of plant extinctions, particularly among species that had evolved in earlier, lower oxygen periods. They simply couldn't keep up with the burning, and the fires didn't just affect plants. Remember those giant insects and arthropods? Those massive dragonflies and millipedes that thrived in the high oxygen atmosphere? They were vulnerable in ways that smaller animals weren't. Large bodies meant slow movement, especially for arthropods whose respiratory systems didn't work well for rapid locomotion. When fires swept through, the giants couldn't escape. Smaller insects could burrow into the ground, hide under rocks, or fly away quickly. The 2-foot-long millipedes and dinner-plate-sized spiders, they burned. Fossil sites that preserve evidence of major fire events show mass death assemblages. Hundreds of large arthropods clustered together, their fossilized remains showing clear signs of burn damage. These weren't animals that died and then burned. These were animals caught by the flames, unable to escape fast enough. The fires also created something else, fire breaks, natural barriers where nothing would grow for years after intense blazes. In a world of continuous forest, these burned zones became corridors of movement for animals that couldn't survive in the dense, oxygen-saturated interior of the coal swamps. Early reptiles, better adapted to drier conditions, began colonizing these fire-created grasslands and scrublands. They were exploiting ecological niches that only existed because of recurring catastrophic fires. But perhaps the most important effect of all this burning was on the atmosphere itself. Every fire released carbon dioxide, lots of it. Fires were consuming organic matter that had taken decades or centuries to grow and releasing all its stored carbon back into the atmosphere in hours or days. This created a natural feedback mechanism that prevented oxygen levels from rising indefinitely. Here's how it worked. More photosynthesis meant more oxygen and more plant biomass. More oxygen meant more frequent and intense fires. More fires meant more plant material burning, releasing CO2 and consuming oxygen. This fire-mediated cycle acted as a kind of atmospheric thermostat, keeping oxygen levels high but not so high that the entire planet would ignite. Climate models of the Carboniferous suggest that without fires, oxygen levels might have climbed as high as 40% or even 45%. At those concentrations, combustion becomes nearly spontaneous. Rocks rubbing together could start infernos. Animal body heat might ignite surrounding vegetation. The planet would have been unlivable. Fires, in other words, saved the world by partially destroying it. They prevented the oxygen crisis from becoming so extreme that it killed everything. They forced evolution to select for fire resistance, creating more resilient ecosystems. They broke up the monotony of endless coal forests, creating habitat diversity. They were catastrophic and essential, destructive and creative, all at once. The geological record shows this fire-oxygen cycle operating on multiple timescales, year-to-year variations in fire frequency, corresponding to wet and dry seasons, decade-scale patterns related to climate oscillations, century-scale cycles where forests would grow, mature, burn and regrow. And over millions of years, the gradual decline of oxygen levels as fire and other factors slowly brought the atmosphere back toward equilibrium. Some of the most dramatic evidence comes from what geologists call fusane deposits. Fusane is fossilized charcoal, and in Carboniferous coal beds, it's everywhere. Not just scattered fragments, but layers of it, sometimes feet thick. These represent catastrophic fire events that consumed entire forest systems. When researchers examine these deposits under microscopes, they can see preserved cellular structures of the wood that burned, frozen in the moment of combustion. What they find is terrifying. Burn temperatures that exceeded 1,200 degrees Celsius. That's hot enough to melt aluminum, far hotter than any modern wildfire. At those temperatures, wood doesn't just burn, it vaporizes. The flames would have been visible from space, massive conflagrations that turn night into day across hundreds of square miles. And these weren't rare events. The fusane layers occur repeatedly throughout Carboniferous rock sequences, sometimes separated by only a few feet of coal. This suggests fire return intervals of maybe a few centuries. That's incredibly frequent by geological standards. For comparison, modern boreal forests have fire return intervals of 50 to 200 years. Carboniferous forests were burning more often and far more intensely. The impact on carbon cycling was enormous. All that carbon that plants had worked so hard to pull out of the atmosphere and lock away in wood and roots. Fire was putting it right back. Estimates suggest that fires were releasing billions of tons of carbon dioxide every year, offsetting maybe 20 to 30% of all the carbon being buried in coal deposits. This created a dynamic equilibrium between carbon storage and carbon release, between cooling through carbon burial and warming through fire emissions. It also created opportunities. Burned areas provided nutrients. All that ash, rich in minerals that had been locked up in plant tissue, was suddenly available. Phosphorus, potassium, trace elements. The immediate post-fire environment was incredibly fertile. Plants that could colonize quickly after fires had massive advantages. This drove the evolution of fast-growing, fire-adapted species that could boom in the aftermath of catastrophe. Animals adapted too. There's evidence that some early tetrapods, the first four-legged vertebrates, developed behaviors for surviving fires. Fossilized burrows from the Carboniferous show signs of being used repeatedly, possibly as refuges during fire events. Some amphibians appear to have become semi-aquatic, partly as a fire survival strategy, retreating to water when flames approached. But the constant burning also created intense evolutionary pressure. Species that couldn't adapt went extinct. Lineages that had dominated in the early Carboniferous, when oxygen was rising but fires were less frequent, disappeared as fire regimes intensified. The late Carboniferous fossil record shows increasing turnover, more extinctions, more rapid evolutionary change. The burning world was forcing life to adapt or die. And through it all, the fires continued. Lightning strikes igniting new blazes every day. Firestorms racing across the landscape at speeds that would terrify modern firefighters. Flames climbing hundreds of feet into the air, creating their own weather patterns, their own winds. Smoke plumes that would have been visible for hundreds of miles, darkening skies and raining ash across entire regions. This was Earth at 35% oxygen. Not a paradise of giant insects and endless forests, but a world in constant crisis. A world where life flourished and burned in equal measure. A world where the very abundance of oxygen, that essential ingredient for complex life, created conditions that constantly threatened to destroy everything. The burning world of the Carboniferous lasted for over 60 million years. Then, slowly, things began to change. The fires had done their work. They'd prevented oxygen from rising to catastrophic levels. They'd driven evolution in new directions. They'd created ecological diversity through destruction. But they were also setting the stage for the next great transformation in Earth's history. The oxygen levels were about to fall, and when they did, it would reshape life on Earth once again. But nothing lasts forever, not even an atmosphere. For 80 million years the world had been running on 35% oxygen. Giant insects ruled the skies. Arthropods the size of alligators patrolled the forest floors. Wildfires burned with an intensity that would make modern infernos look like candle flames. The coal forests stretched across entire continents, pumping oxygen into the atmosphere at rates never seen before or since. Then something changed. Something small at first, microscopic even, but it would ultimately bring down the entire oxygen-rich world that had dominated Earth for longer than dinosaurs would later rule. Around 290 million years ago, deep in the rotting wood of a fallen tree somewhere in what is now Europe or North America, a fungus evolved a new ability. Not just any ability, the ability to break down lignin. Now, this might not sound revolutionary, but remember, lignin was the reason oxygen levels had gotten so high in the first place. It was the molecular fortress that made wood essentially indestructible. Trees had been falling and accumulating for 80 million years because nothing could eat them. All that undecomposed wood meant all that carbon stayed locked away, and all that oxygen stayed in the atmosphere. The fungus that cracked the lignin code was probably something similar to modern white rot fungi. It evolved a suite of specialized enzymes, peroxidases and lacases, that could break the chemical bonds holding lignin molecules together. These enzymes worked like molecular scissors, cutting apart the complex aromatic rings that made lignin so stable. At first, this single evolutionary innovation probably seemed insignificant. One species of fungus in one forest, being able to digest wood slightly better than its competitors. But natural selection doesn't care about maintaining atmospheric oxygen levels. It only cares about who survives and reproduces. And fungi that could eat wood had just gained access to the largest food source on the planet. They spread, not quickly by human standards, but inexorably. Fungal spores drifted on wind currents, hitched rides on insects, floated across oceans. Wherever trees grew, these lignin-degrading fungi eventually arrived. And once they arrived, they multiplied. Within a few million years, which is basically nothing in geological time, white rot fungi had spread across every forested region on Earth. Dead trees that once would have remained intact for centuries now decomposed within decades. Fallen logs that should have formed the foundation of future coal deposits were being consumed by fungal mycelium, broken down into simpler compounds, their carbon released back into the atmosphere as carbon dioxide. The Great Carbon Sink was springing leaks, but white rot fungi weren't alone. They were followed closely by brown rot fungi, which evolved a different strategy for dealing with lignin. Instead of breaking it down completely, brown rot fungi modified lignin's structure just enough to access the cellulose locked inside. They left behind chemically altered wood that crumbled into fragments, which could then be processed by bacteria and other decomposers. Together, these fungi revolutionized the carbon cycle, and in doing so, they began the slow process of bringing oxygen levels back down. Think about the scale of this change. For 80 million years, forests had been net oxygen producers on a scale that modern ecosystems can't match. Trees grew, died, and were buried before decomposition could return their carbon to the atmosphere. It was like a one-way valve, constantly pulling carbon dioxide out of the air and pumping oxygen in. Now the valve had reversed. Dead wood was being decomposed at roughly the same rate it was being produced. The carbon that trees pulled from the atmosphere during their lives was being released back when they died. The system had reached equilibrium, and equilibrium meant oxygen levels would start to fall. But the fungal revolution was just the beginning. The entire structure of Earth's plant communities was about to undergo a transformation that would accelerate the oxygen decline and fundamentally reshape the planet's ecosystems. The coal forests, those vast swamps dominated by scale trees and giant horsetails, had thrived in consistently wet, low-lying environments. They needed standing water, high humidity, stable conditions. For tens of millions of years, much of the supercontinent that would become North America and Europe had provided exactly those conditions. Then the climate began to shift. Around 290 million years ago, Earth entered what geologists call the Permian period. The climate was becoming more seasonal, more variable. Some regions were getting wetter, but many were becoming much drier. The endless coastal swamps that had nurtured the coal forests were shrinking, being replaced by better drained upland environments. The scale trees couldn't adapt. They were too specialized, too dependent on their specific swamp conditions. As their habitats contracted, so did their populations. Vast regions that had been covered in dense lepidodendron forests for millions of years were transforming into more open woodlands dominated by different plants entirely. Seed ferns were taking over, along with early conifers. These new plants were better adapted to seasonal climates and drier conditions. They had developed more efficient water transport systems, better drought resistance, more flexible growth patterns. They were the future of forests, but they were also much less productive at generating oxygen. Seed ferns and early conifers didn't grow as fast as scale trees. They didn't produce as much biomass per acre. Their wood, while still substantial, wasn't being buried in oxygen-free swamps where it would form coal. Instead, it was falling onto drier ground where fungi and bacteria could decompose it relatively quickly. The great coal-forming period was ending, and with it, the primary mechanism that had driven oxygen to 35% was shutting down. The geological record from this period tells the story clearly. Coal deposits, which had been forming continuously across vast regions for 80 million years, suddenly become much rarer. The Permian has some coal, but nothing like the massive deposits of the preceding Carboniferous period. The carbon that should have been locked underground was staying in the active carbon cycle, being recycled through living organisms, keeping atmospheric carbon dioxide levels higher and oxygen levels lower. But there was another factor at play, something even more fundamental than fungal evolution or changing plant communities. The entire planet was being reshaped by tectonic forces that would have profound effects on global climate and oxygen production. Pangaea was forming. For hundreds of millions of years, Earth's continents had been scattered across the globe, separated by vast oceans. But plate tectonics was slowly bringing them together. By 275 million years ago, almost all of Earth's landmass had collided to form a single supercontinent, Pangaea, stretching from pole to pole. This geographic reorganization fundamentally changed how Earth's climate system worked. With all the continents jammed together, the total length of coastline decreased dramatically. Coastal regions are crucial for oxygen production, because that's where shallow marine environments support massive populations of photosynthetic plankton and algae. Less coastline meant less productive coastal ocean, which meant less oxygen being pumped into the atmosphere from marine sources. Even more importantly, Pangaea's formation created vast interior regions that were thousands of miles from any ocean. These continental interiors developed extreme climates, hot and dry, with massive deserts that would make the Sahara look tiny. Desert ecosystems produce almost no oxygen. No dense forests, no thick vegetation, just scattered drought-adapted plants struggling to survive in harsh conditions. The interior of Pangaea became a biological dead zone. Hundreds of millions of square miles that could have been covered in oxygen-producing forests instead became barren wastelands, where little grew and even less could survive. The mountain building associated with continental collision also affected oxygen levels. When continents crash together, they push up massive mountain ranges. The formation of Pangaea created mountain chains that would have dwarfed the modern Himalayas. These mountains disrupted atmospheric circulation patterns, created rain shadows that expanded deserts, and locked up huge amounts of water in permanent ice caps. Weathering of these new mountains also played a role. When fresh rock is exposed by mountain building, it begins to weather, reacting with atmospheric carbon dioxide and oxygen. This chemical weathering pulls oxygen out of the atmosphere and locks it up in oxidized minerals. The faster mountains erode, the more oxygen gets consumed in these weathering reactions. During Pangaea's formation, erosion rates were extraordinarily high. All those fresh mountain ranges were being attacked by wind and water, their rocks breaking down and reacting with the atmosphere. This created another drain on atmospheric oxygen, one that would continue for millions of years. But perhaps the most dramatic factor in oxygen's decline was yet to come. The end of the Permian period, about 252 million years ago, brought the greatest mass extinction in Earth's history. Not just the extinction of dinosaurs famous, but far worse. Over 90% of all species on Earth died. The causes of the end Permian extinction are still debated, but the leading theory involves massive volcanic eruptions in what is now Siberia. These weren't ordinary volcanoes. They were flood basalts, eruptions so enormous they covered an area the size of the continental United States, with lava up to 2 miles thick. The Siberian Traps eruptions release staggering amounts of carbon dioxide, methane and sulfur dioxide into the atmosphere. Global temperatures spiked by as much as 15 degrees Celsius. Ocean chemistry changed dramatically, becoming more acidic and losing much of its dissolved oxygen. Ecosystems that had been stable for millions of years collapsed within a few thousand years. The extinction was selective, but devastating. The remaining coal forest species, already in decline, were wiped out almost entirely. Many groups of marine organisms that had been primary oxygen producers went extinct. The complex ecosystems that had developed during the high oxygen period were shattered, replaced by much simpler communities dominated by a few hardy survivor species. In the aftermath of the extinction, oxygen levels plummeted. Some estimates suggest they dropped to around 15%, lower than modern levels. The high oxygen world was over. Earth was entering a new phase, one that would eventually lead to the rise of dinosaurs and, much later, mammals. But the transition wasn't instantaneous. It took millions of years for oxygen levels to decline from their Carboniferous peak to Permian lows. Throughout this period, ecosystems were constantly adjusting to changing atmospheric conditions. The giant insects were among the first casualties. As oxygen levels dropped below 30%, the very largest arthropods began to struggle. Their respiratory systems, so efficient in high oxygen environments, became limitations in a world with less available oxygen. Maximum insect size began to shrink. The dragonflies with 2-foot wingspans became scarce, then vanished entirely. The Megafauna, those eagle-sized predatory insects that had ruled the skies for tens of millions of years, went extinct around 270 million years ago. Not because anything hunted them to extinction, but because the atmosphere literally couldn't support them anymore. They suffocated in an air that would have seemed perfectly breathable to modern animals, but was fatally thin to creatures adapted to 35% oxygen. The terrestrial arthropods followed a similar pattern. Arthropleura, those 6-foot millipedes, disappeared from the fossil record. The giant scorpions and oversized spiders declined and vanished. Not all at once, but steadily, inexorably, as the world they'd evolved for ceased to exist. In their place, new groups began to rise. Vertebrates, which had been present but relatively small and insignificant during the high oxygen period, began to diversify and grow larger. Early reptiles developed more efficient respiratory systems with lungs that didn't depend on passive diffusion. They could survive and thrive at lower oxygen levels that would have been fatal to their amphibious ancestors. The therapsids emerged, mammal-like reptiles that would eventually give rise to true mammals. These creatures had metabolic systems capable of generating substantial body heat, which required efficient oxygen use. They weren't as impressive as the giant insects they were replacing, but they were better adapted to the new atmospheric conditions. By the end of the Permian, 252 million years ago, oxygen levels had stabilized around 23%, not too far from modern concentrations. The age of giants was over. Earth's atmosphere would never again reach such extreme oxygen levels. The unique combination of circumstances that had created the high oxygen world, newly evolved woody plants, lack of decomposers, vast swamp forests, had been a one-time event in Earth's history. The fungi had seen to that. Once lignin decomposition evolved, it couldn't be unevolved. The genetic information was out there, spreading through fungal populations, being refined by natural selection. Wood would never again accumulate in vast oxygen-producing deposits. The carbon cycle had closed its loop. But the legacy of that high oxygen period would persist. The coal deposits formed during those 80 million years would lie buried for hundreds of millions of years, waiting. Eventually, much later, a new species of primate would discover them, dig them up, and burn them, releasing in a few centuries the carbon that had taken 80 million years to bury. But that's another story. For now, as the Permian drew to a close, Earth was entering a new phase, a more balanced phase, where oxygen levels would fluctuate within a narrower range, where no single group of organisms would dominate so completely, where atmospheric composition would be determined by the complex interplay of countless species rather than the unchecked growth of coal forests. The Great Decline had brought the oxygen revolution to an end, but it had also set the stage for the next great chapter in Earth's history. The age of dinosaurs was coming, and after them, the age of mammals, and eventually the age of humans. All of it possible because oxygen levels had dropped from their deadly, fire-prone giant insect-supporting peak back down to something that complex warm-blooded vertebrates could survive in. Sometimes decline isn't failure. Sometimes it's just the universe correcting course, finding a new equilibrium that opens up possibilities that weren't available before. So here's where the story gets personal. Because that ancient world of 35% oxygen, those giant insects and endless coal forests, they're not just some fascinating curiosity from deep time. They're literally part of your life right now, every day, in ways you probably haven't considered. Let's start with the most direct connection. That coal we've been burning for the past 200 years to power our civilization, the stuff that drives our power plants, that fueled the Industrial Revolution, that still provides about 27% of global electricity. That's them. That's the Carboniferous forests. Every lump of coal is the compressed, transformed remains of those giant lepidodendron trees and their relatives, trees that grew so abundantly, so impossibly fast in that high oxygen world that they buried carbon faster than it could decompose. Think about that for a second. When you turn on a light powered by coal, you're releasing energy that was captured from sunlight 300 million years ago. Energy that was stored by trees that grew in an atmosphere so rich in oxygen that dragonflies the size of hawks patrolled the skies. You're literally burning the Carboniferous period, taking carbon that was locked away in an ancient greenhouse and releasing it back into the atmosphere where it came from. But here's the thing that makes this really wild. Those forests didn't just create coal, they fundamentally changed Earth's atmosphere. By pulling so much carbon dioxide out of the air and burying it underground, they transformed the entire planet. They ended a greenhouse world and created the conditions for ice ages. They set up the modern carbon cycle. They made Earth into the kind of planet where mammals and eventually humans could thrive. And now we're undoing that work. Every ton of coal we burn releases carbon that those ancient forests worked for millions of years to sequester. We're running the Carboniferous in reverse, taking carbon that was safely locked away and pumping it back into the atmosphere as carbon dioxide. In about 200 years, we've released a significant fraction of the carbon that took 60 million years to bury. The Carboniferous forests couldn't have predicted this. Evolution doesn't plan ahead. Those trees were just doing what trees do, growing, reproducing, competing for sunlight. They had no idea they were building the fuel source for a future civilization. No concept that their bodies would one day power electric grids and factories and transportation systems across an entire planet. But that's exactly what makes this period so important for understanding our current climate situation. The Carboniferous teaches us that atmospheric composition isn't fixed. It's not stable. It can change dramatically over relatively short geological timescales. And when it changes, everything else changes with it. The oxygen surge to 35% happened over about 50 million years. Fast in geological terms, but incredibly slow by human standards. Ecosystems had time to adapt. Species evolved new body plans to exploit the new conditions. the planet's regulatory systems gradually adjusted. Then oxygen declined again, falling back toward modern levels over another 50 million years. Again, slow enough for life to adapt gradually. What we're doing now is different. We're changing atmospheric composition on timescales of decades, not millions of years. The carbon dioxide increase we've triggered is happening about 100 times faster than anything in the geological record outside of massive volcanic eruptions and asteroid impacts. This isn't giving life time to adapt gradually. This is shocking the system. And the Carboniferous teaches us something else crucial. Earth's atmosphere is regulated by life itself. It's not just a passive chemical mixture. It's an active, dynamic system where living things control what gases are present and in what concentrations. Those Carboniferous forests didn't just respond to their environment, they changed it. They created the conditions that ultimately led to their own decline. This is what scientists call a feedback loop. High oxygen and low carbon dioxide created conditions that favored different types of plants. These new plants were less effective at burying carbon. So carbon dioxide began increasing again, and oxygen began falling. The system self-corrected over tens of millions of years. Our planet has these regulatory mechanisms built in. Weathering of rocks pulls carbon dioxide out of the atmosphere over geological time. Volcanic activity releases it back. Photosynthetic organisms produce oxygen. Respiration and decay consume it. Over long time scales, these processes balance out, keeping the atmosphere within ranges that can support complex life. But here's the terrifying part. These regulatory systems work slowly. They're geological processes operating on timescales of millions of years. They can't respond quickly to rapid changes. So when we dump billions of tons of carbon dioxide into the atmosphere in just a couple of centuries, the planet's natural regulatory systems can't keep up. We're overwhelming them. Could oxygen levels rise again? Could we somehow engineer our way back to a 35-cent oxygen world? Technically, yes. Life did it once. But the practical answer is no. Not without fundamentally transforming the entire planet, and we wouldn't want to anyway. Because remember what their world was like. Imagine modern Earth with 35% oxygen. First, you'd notice breathing felt easier. Your body would be flooded with oxygen. You'd feel energized, at least initially. But then the problems would start. Oxygen is toxic in high concentrations. It damages cells through oxidative stress. At 35%, you'd be experiencing chronic oxygen toxicity. Your lungs would start deteriorating. Your nervous system would malfunction. You'd probably develop symptoms similar to oxygen toxicity that divers experience when breathing high-pressure gas mixtures. Insects, though, insects would explode in size. Modern insects are limited by oxygen availability. Increase atmospheric oxygen, and you remove that constraint. Within a few thousand generations, you could have dragonflies with 2-foot wingspans again, beetles the size of rats, centipedes as long as your leg. The ecological consequences would be catastrophic. Modern ecosystems are balanced for 21% oxygen. Change that, and everything changes. Food webs would collapse. Species that couldn't adapt fast enough would go extinct. New diseases would emerge as microbes adapted to the new conditions, and fires, the whole planet, would become a tinderbox. Wildfires would rage on scales that would make current megafires look like campfires. This is why Earth's atmospheric regulation is so crucial. Life has evolved for the current conditions. The current oxygen level isn't arbitrary. It's the result of billions of years of evolution and planetary feedback mechanisms. It's high enough to support complex animal life, but low enough to prevent constant global firestorms. It's a sweet spot, and we're in it. But studying the Carboniferous helps us understand exactly how delicate this balance is. That period teaches us that planetary atmospheres can change, that life adapts to new conditions but not instantly, that there are consequences, sometimes catastrophic ones, when atmospheric composition shifts too quickly. This knowledge is crucial for understanding climate change. When people say climate changed in the past and life survived, they're right, but they're missing the context. Yes, oxygen went from 21% to 35% and back down again. Yes, life survived. But it took 100 million years, and countless species went extinct during the transitions. Entire ecosystems collapsed and reformed. The world that emerged after each transition was fundamentally different from the world that came before. We're triggering changes on similar scales, but we're doing it in centuries instead of millions of years. That's the difference. That's why biologists are terrified. Evolution needs time to work. Ecosystems need time to adjust. We're not giving them that time. The Carboniferous also teaches us about tipping points. For millions of years, forests buried carbon and oxygen rose gradually. Then something changed. Maybe it was the evolution of fungi that could break down lignin. Maybe it was changing climate patterns that reduced swamp areas. Probably it was a combination of factors. But once the system reached a tipping point, it shifted rapidly to a new state. Oxygen began falling. Carbon dioxide began rising. The coal forests gave way to different ecosystems. Tipping points are terrifying because you don't know you've reached one until you've passed it. This system seems stable, then suddenly it's not. It shifts to a new state, and there's no easy way to shift it back. Understanding how Earth's atmosphere crossed tipping points in the past helps us identify where modern tipping points might be, where the changes we're making might trigger rapid, irreversible shifts in climate or ocean chemistry or ecosystem function. This knowledge extends beyond Earth. When astrobiologists search for life on other planets, one of the key biosignatures they look for is oxygen. Because free oxygen in an atmosphere is almost certainly produced by life. Oxygen is too reactive to persist on its own. It combines with other elements too readily. If you detect significant oxygen in an alien atmosphere, something must be continuously producing it, and the most likely candidate is photosynthetic life. The Carboniferous shows us that oxygen levels can vary wildly on living worlds. An exoplanet might have 10% oxygen, or 35%, or anywhere in between, and still support complex life. This expands the range of potentially habitable worlds. We don't need to find exact Earth analogues. We just need to find worlds where life is actively managing atmospheric composition. It also suggests what kinds of life might be possible on high oxygen worlds. If we find a planet with 35% oxygen, we should expect gigantic arthropods. Physics doesn't change. The same constraints that limited insect size on ancient Earth would apply elsewhere. High oxygen equals bigger bugs. Always. But perhaps the most important lesson from the Carboniferous is this. Life is incredibly adaptable, but planetary systems are interconnected in ways we're still trying to understand. Those ancient forests didn't set out to change the world. They just grew. But by growing in such abundance, they triggered a cascade of changes that transformed everything. Climate, wildfire frequency, ocean chemistry, the size of insects, the evolution of reptiles, everything connected to everything else. We're doing the same thing now. We're burning fossil fuels just trying to power our civilization. We're not intentionally trying to change the planet. But by releasing carbon on such massive scales, we're were triggering cascades of changes that we're only beginning to understand. Rising temperatures, shifting rainfall patterns, ocean acidification, changes in atmospheric circulation, species extinctions, all connected, all feeding back on each other in complex ways. The Carboniferous took millions of years to play out. Our changes are happening in decades. That's the critical difference. That's why this matters. Earth systems can handle gradual changes. Life adapts. Feedbacks kick in. The planet regulates itself. But rapid changes overwhelm these regulatory mechanisms. The system can't stabilize itself fast enough. This is what keeps climate scientists up at night. Not that change is happening. Change always happens. But that it's happening too fast for the planet's natural regulatory systems to compensate. We're pushing Earth toward a new state, and we don't fully understand what that state will look like. The Carboniferous shows us that when atmospheric composition changes dramatically, everything changes. Ecosystems restructure, species go extinct, new life forms emerge to fill new niches. The world that comes out the other side is fundamentally different. And here's the final lesson. The Carboniferous forests locked away carbon for 300 million years. That carbon was safely sequestered underground, out of the climate system. It couldn't affect atmospheric composition. It couldn't drive warming or cooling. It was done, finished, removed from the active carbon cycle until we came along and dug it up. In doing so, we've reactivated carbon that the planet had already dealt with. We've brought it back into play. Those ancient forests did their job. They pulled excess carbon out of the atmosphere and buried it. They created the conditions for modern life to evolve. And we're undoing that work, releasing it all back, running the experiment in reverse. The question now is whether we're smart enough to recognize what we're doing and stop before we trigger changes we can't control. The Carboniferous teaches us that planetary atmospheres can be managed, that life itself is the primary force controlling atmospheric composition on living worlds. The question is whether intelligent life, our kind of life, can manage atmospheres consciously, whether we can choose to regulate our impact the way Carboniferous forests regulated theirs accidentally. We're the first species in Earth's history with the ability to understand these processes, to see the connections between what we do and how the planet responds. The Carboniferous forests couldn't have known they were changing the world, but we know. We can see it happening in real time. The question is what we do with that knowledge. That's the real legacy of the high oxygen world. Not just giant insects and coal forests, but a lesson about planetary management written in rocks and fossils and ancient atmospheres. A reminder that what we do matters, that changes compound, that the planet is a system, not a collection of separate parts, and that sometimes the most important legacies are the ones we leave buried underground. So here we are. After travelling through 60 million years of Earth history, after watching dragonflies the size of hawks hunting through primeval forests, after witnessing fires that burned with such intensity they created mountains of coal, after exploring a world where the very air was fundamentally different from what we breathe today, we need to ask ourselves, what does it all mean? Because here's the thing about that 35% oxygen atmosphere. It wasn't just a quirk of ancient chemistry. It was a complete restructuring of what life could be, of what was physically possible on our planet. Every breath taken by a Carboniferous millipede was richer, more energizing than anything we'll ever experience. Every fire that ignited burned hotter and spread faster. Every evolutionary pressure, every survival challenge Every adaptation was shaped by an atmosphere we can barely imagine. Think about the facts we've covered. Dragonflies with 2.5-foot wingspans patrolling ancient swamps. Millipedes 8 feet long crawling through undergrowth that would tower for modern forests. Amphibians as large as crocodiles, supported by oxygen levels that made their inefficient breathing systems viable. This wasn't science fiction. This was Earth, our Earth, the same planet we're standing on right now, just at a different point in its 4.5 billion year story. And those coal forests. Think about this for a second. Those trees that couldn't decay properly, that piled up century after century, millennium after millennium, eventually became the coal that powered the Industrial Revolution. When you turn on a light switch powered by a coal plant, you're literally using energy from sunlight that fell on Earth 300 million years ago. Energy captured by plants that evolved in that high oxygen world, that grew in those strange forests where nothing could break them down after they died. The fires, though, that's what really captures the scale of how different things were. Modern wildfires are terrifying enough, but Carboniferous fires burned with such intensity that they could consume entire landscapes in hours. They created their own weather patterns. They left charcoal deposits so thick that geologists find them in rock layers worldwide. The evidence of atmospheric oxygen levels is literally baked into the geological record. But what's most profound is what happened next. The oxygen didn't stay at 35% forever. It couldn't. The very processes that created those conditions, the burial of organic carbon, the expansion of plant life, eventually triggered feedback mechanisms that brought oxygen levels back down. By the Permian, by the time of the Great Dying 252 million years ago, oxygen levels had dropped significantly. The age of giant arthropods was ending. A new world was being born. This is what deep time teaches us. Nothing stays the same. Earth's atmosphere, which seems so permanent, so unchanging from our human perspective, has actually been in constant flux for billions of years. It's been mostly nitrogen and carbon dioxide. Then it became oxygen-rich through bacterial photosynthesis. Then it spiked to 35% during the Carboniferous. Then it dropped again. Now we're changing it ourselves through industrial emissions, adding carbon dioxide at rates not seen since those ancient times. We are living through another atmospheric transformation, just on human timescales instead of geological ones. And understanding what happened during the Carboniferous, how the atmosphere and life co-evolved, how changes in one drove changes in the other, that gives us context for understanding our own moment in Earth's history. Because we're not separate from this story, we're part of it. Every human alive today is breathing an atmosphere that was shaped by billions of years of life interacting with the planet. The oxygen in your lungs right now was produced by photosynthetic organisms. The nitrogen was processed through countless bacterial cycles. Even the trace gases, the argon and carbon dioxide and everything else, they're all products of geological and biological processes stretching back to Earth's formation. We are quite literally breathing deep time. So as you drift off to sleep tonight, think about this. You are one small part of an unimaginably vast story. A story that includes dragonflies the size of hawks, and forests that couldn't rot and fires that could burn underwater. A story that spans hundreds of millions of years and will continue for hundreds of millions more. A story where the very air changes composition, where life adapts to conditions we can't even imagine, where extinction and innovation cycle endlessly through deep time. If you've made it this far, if these stories of ancient Earth have captured your imagination, I'd love to hear from you. Drop a like if you enjoyed this journey through the Carboniferous. Leave a comment letting me know where you're listening from, whether you're falling asleep or wide awake, imagining giant millipedes crawling through coal forests. And subscribe if you want more stories from Earth's deep history, more journeys through the vast stretches of time that made our world what it is today. Sleep well, dream of ancient skies, and remember, you're breathing the same planet that once breathed at 35% oxygen. The Earth endures, life adapts, and the story continues.